Hello class, and welcome to an introduction into finding the second derivatives implicitly. So before we can take the second derivative, we have to of course take the first derivative. So review that implicitly this will give us 2x, and then I took the derivative of x with respect to x, plus 2y, the derivative of y with respect to x, will equal 0. And so now we want to solve for what is dy dx equal, and of course that means 2y dy dx will equal negative 2x, and so the derivative of y with respect to x will be equal to negative 2x over 2y, and when we clean that up, that means that that first derivative is simply the opposite of x divided by y. Okay? On the next slide, we'll start taking the second derivative. So we know we have this. Now we're going to take the derivative of that. So on this side, we're going to take the derivative of dy dx, and on that side, we're going to start taking the derivative of that quotient. So we have to do a quotient rule, and it's going to be the bottom, which is the y value, times the derivative of the top, which is negative 1, and that was a derivative of x with respect to x, so I don't need to write that. And then we'll subtract the top, the top, which is opposite of x, times the derivative of the bottom, which is dy dx. And then we divide that by the bottom squared. I'll turn my attention to the left side here. The derivative d dx of dy dx, the d's are what end up getting squared. So the way we write this notation for the second derivative is it's d squared of y, because notice there's only one y in that numerator. So when I look at this, you notice there's only one y there, but there's two d's. So that's why it's d squared and just one y. Hopefully I can clean that up a little bit for you so that you can read it. Let's see. Trying to. It's not letting me erase. Okay. Well, there's always a second way to do it, and it's not letting me do that either. Okay. Over. Now in the denominator, we have dx, and we have that twice, so we write it afterwards as dx, that whole thing squared. Over here, we just clean up to be the opposite of y, plus x times dy dx over y squared. Now, this is pretty good, except for we have the second derivative solved for, but in the first derivative, we have on this side, we have a first derivative that's written in that notation. So I want to substitute what that is in there, and I want to replace it with the opposite of x divided by y. And we'll go back and we'll try to write this cleaner this time. So the second derivative of y with respect to x both times is equal to the opposite of y plus x times that quantity over y squared. Now this is screaming that it needs to be cleaned up because this is a complex fraction. So on this slide, maybe I can fit one more cleanup in here that I need to get in the numerator, the same denominator. So I'm going to multiply this one by y over y, and that will lead us to the idea that, and I don't know that I can manage my space here, but we're going to try it here. Second derivative of y with respect to x both times is equal to the opposite of y squared plus x times negative x is the opposite of x squared, and that's all divided by y, and that's all divided by y squared. So if you're comfortable with your complex fractions, you're going to multiply that by 1 over y squared, and we'll be left with the opposite of y squared minus an x squared all over y cubed. And at this point, that is pretty good because you've done your complex fraction skills and you've found an answer for d squared y. However, matching your answer in the back of the book, that won't be enough, and to get the bonus point for your algebra skills, that won't be enough. So we need to do some more back substituting. Although this is correct so far, and there's a couple things you can do from here. Let's look at the next slide, and we're going to show you a trick that you can always do on the second derivative. Once I've found that second derivative, I can always find my original equation some back substitution. So you'll notice that in the upper right hand corner we have the original thing, and I want to look for x squared plus y squared, and I want to somehow replace it with 25, or I want to look for one side of the equal sign and replace it with the other. So when I look up here, I see that we have the second derivative with respect to of y with respect to x both times should be equal to -1 times the quantity of y squared plus x squared all over y cubed. And there you should see that we have an x squared plus y squared in the parentheses, and that I'm going to replace with the number 25. And so, sorry about the handwriting, it's not used to writing with this stylus on here, over y cubed, and then we put this in as 25, and we have a second derivative. And why that's nice to do is because this original second derivative is dependent on both the x value and the y value. Okay? Now we have a second derivative where we can predict it solely on what the y value is, and that will tell us the second derivative with just one thing in there, and that is the y value. Okay? Hope this gives you an idea. That's what you're trying to do on second derivatives. Again, it's just take the first derivative, and then take the second derivative, substitute the first derivative back in, do some algebra, and then if you can do the rest of the algebra, you can resubstitute to clean it up even more. That's how you can get all those problems. Good luck on finding your second derivatives, and stay tuned for the next slide on the introduction to related rates.